So this is problem 2, practical kinematics 2, and the train on the circular track, as shown in the figure there, travel at 50 feet per second, and the train on straight track traveling 20 feet per second. So there are two portions of the problem. The A is what is the velocity of passenger A on the train A, right, on the train track, and then passenger B on the circular track. So this is the relative velocity. So we can start with writing the relative velocity equation. So problem 2A. So relative velocity equation, we have V, in this case, they ask passenger A relative to B. So you have to start with A, VA equal to VB plus VA relative to B, not VB relative to A. Keep that in mind. And VA, basically, that is the passenger A on the straight track train, the train on the straight track, and that velocity is 20 feet per second going down. So we can draw the diagram for that one. So VA, and we use components and scalar equation. So that you can see here, you have VA is 20 feet per second, and that basically VA. And again, it equal to VB. VB at the point B here. And if you recall, point B at that point is tangent to the path, the velocity tangent to the path. So at that point, it should be vertical going up. So VB, if you see what I show on the graphic there. Make sense? So with that, in the diagram, it will be go up, VB equal to, because tangent to the path, it means perpendicular to the radius. In that case, the radius horizontal, VB go vertical. And that will be 50 feet per second. 50 feet per second. Plus VA relative to VB. And again, we don't know what is those two components. And that's what we are want to looking for. So we can break it down into X and Y components. So VA relative to B. VA relative to B, X components, and VA relative to B, Y components. And we assume positive X and Y as usual. And we break it down into components and solve, right? So let's do it here. As you can see, in X components, I assume go to the right positive. So VA vertical, so you see 0 equal to VB going up, but we have x-axis, so it's 0 plus VA relative to B, x. So from that, you can have X components of relative velocity of passenger A on relative to passenger B equal to 0 in X components. Similarly, in Y components, we have scalar equation is, I assume going up positive, so it will be negative 20 equal to positive 50 plus, we assume VA relative to B in Y component going up, so it's positive. From that, we can have VA relative to B in Y components equal to 70 negative. Okay, on the side. So what does that mean? It will be opposite to our assumed direction. In Y components of relative velocity of A over B going up, that is our assumption. So it should going down because we find out that is a negative answer here. So 70 feet per second going down. And you can see the X component is 0, Y component is 70 going down. So of course the answer should be the relative velocity of A relative to passenger B on the other train equal to 70 feet per second and going down. And that is the first answer of this problem. So let's move on to the second components of this problem. And the component of this problem is the trains. Again, the same information in terms of velocity. 50 feet per second for the one on the circular track, 20 feet per second for the one on straight track. But they give you additional information which is increasing the speed 2 feet per second for the one on straight track. So increasing, when the acceleration is increasing, it means the direction of that acceleration should be similar to the direction of the motion. So what does that mean here? As you can see, the straight track going down, so the motion is going down, the acceleration, the train is in accelerating because it's increasing speed, so it will be same as the motion. So as you can see, A of train A equal to 2 feet per second square. And you can see that in the graph that I show. So when it increases in speed, the acceleration is same as the motion. If it decreasing or deaccelerate, then the acceleration should be opposite of the motion. Okay, so with that, let's go to the relative acceleration of passenger A relative to B. So now let's do with the equation. I have A equal to AB plus A relative to B, and we can draw the diagram AA. So as you can see, I already showed it's same motion, 2 feet per second, so it will going down same as the motion. AA equal to 2 feet per second, 2 feet per second square, because this is acceleration. And then it equal to AB. Now B, as you can see, it's constant on the circular track. But remember, B, the train on the circular track, it will have a curvilinear motion. What is curvilinear motion? Go to review the practical kinematic ones. So there are two components of acceleration. Tangential, in this case, it have a constant speed. So the tangential components equal to dv over dt equal to 0. So it's only the normal components. The normal component here of the train B, so this is, as you can see, AB, normal components of AB, and that equal to VB squared over rho, if you recall that, right? So let's go to here, and it will be horizontal direct to the left. So I can have equation here. This actually A, B, but if you want, that is the n components, right? N component you can put up there or going down, and it equal to the one tangential component is 0 because the train on the constant speed 50 feet per second. So here you have it v square over radius, so it equal to 50 square over the radius of circular track is 50 feet as shown in the finger there. So you can have 500 feet. So you have 500. So it will be the number there. And then plus AIB. AIB, you can break it down into again A relative to B, X, and A relative to B, Y, and we assume again X and Y components. And with that, we can do this exactly the same in X component and Y component. So let's write out X components, positive, go to the left, go to the right. So it will be A vertical, so it will be 0 equal to, this one is 5 feet per second square. So you have that one here is negative 5 plus a relative to b x. From there I can have a relative to b x equal to 5 feet per second square, and if positive it means go to the right. And similarly I have y, I assume going up, it will be negative 2 for AA because it's going down, and then AB horizontal, so vertical projection, it will be 0, plus AA relative to BY. So from that I can have A relative to B in Y components equal to negative 2 feet per second square, or if you want it will be 2 feet per second square going down. So from that we can have, if we use Cartesian form of the relative velocity vector of A, passenger A, relative acceleration of passenger A relative to passenger B on the other train, it will be equal to 5 for x, negative 2 for y components, and the unit is feet per second square. And that box the answer for this components problem.